Hey folks, in this screencast, we're going to discuss Newton's three laws. These are the three ideas that he posited in Principia Mechanica, his landmark publication. And with each of these laws, we're going to describe a little bit of nuance. I know that you've seen these before, but hopefully this will add a little bit more depth and understanding before we start tackling the mathematics and deriving equations of motion. So the first law, law number one, says every body perseveres in a state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. Now, this very wordy description here is essentially saying what you've heard before, which is an object in motion remains in motion unless acted on by another force. Now, what that means, or what that meant in the 1700s when Principia was published, is that this is Newton really taking a jab at Aristotle. You see, for over a millennium, people had believed Aristotle, and Aristotle essentially said that when you apply a force to an object, it moves, which gives us this relationship, F equals mv. Now, this isn't a crazy conclusion, because when you make an observation of a system, which we now know is the system state, you see movement, you see position, and you see velocity, or you see speed. And so if you apply force, something moves. We now know that that's incorrect because we have moved on to Newton's second law, and we say that F is equal to ma. And so really what Newton's doing here is making a very bold statement. He's saying motion is motion. Things can be in motion and there doesn't even have to be a force that's being applied to it to cause that motion. Force is only going to change the motion. And that takes us to the second law. So Newton's second law says the alteration of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. And so now we see that if we've rejected F equals mv, then what Newton's second law does is it now gives us the correct, or at least this new formulation, which now we say is F equals ma. Now, I've got to point out that Newton never actually wrote F equals ma. What he wrote was this: the alteration of motion is ever proportional to the motive force impressed, which eventually translated a few decades after that into this idea of F equals ma. But taking that language at its face value, we never actually said F equals ma. In fact, it was the motive force, this F, is equal to the time derivative of mv. So we've seen this before. I'm going to put this in vector notation. So mv is linear momentum, and I hope you've seen this before in physics, but what's actually happening here is that a force is proportional to the time derivative of momentum. The other way to write momentum is going to be d dt, and momentum we also say is a lowercase p. And then the other important point that Newton made was the idea that we need to observe the motion from a particular reference frame. And that reference frame is an inertial reference frame. He ended up calling it fixed according to the stars. And so that means all of our time derivatives need to be observed in the inertial reference frame. So it's the time derivative with the I, superscript I. Our velocity is observed in that reference frame. And by default, if the velocity, which makes up momentum, is observed in the inertial reference frame, then momentum itself has to be observed in the inertial reference frame. Now, one last interesting piece about these first two laws and the concept of an inertial reference frame is that Newton had stated that the frame that we need to observe motion needs to be fixed according to the stars, whatever that means. And we quickly found out, after that was published and people began to run their experiments, is that the first law also defines an inertial reference frame. So this defines what we're going to call I, because an inertial reference frame doesn't have to be fixed. It can be moving. but it has to be moving in a particular way. It has to be moving in a straight line at a constant speed. And so when we observe law number one or read law number one, we read that everybody perseveres in a state of rest or uniform motion in a right line unless it's compelled to change that state by forces impressed thereon. So what this means is that the reference frame that's inertial can't be spinning, it has to be moving in a straight line, and it can't have any forces acting on it, which we're essentially saying it can't be accelerating. And this is the concept that's now known as Newtonian relativity. And then finally we have Newton's third law. And this is saying to every action there is always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. You've taken a statics course, so you are intimately familiar with how this works. If you have a force in one direction and a force in another direction between two objects, it's going to be the same force. And one last thing to point out is the existence of a force. Because the idea of a force is something that we all believe in, we experienced it, we can measure this, but to actually develop the force from a principled standpoint, ground up, is really hard to do. And there's a good section in your book on different theories of force and how that works. And it's interesting that when Newton even mentioned force, he wasn't actually able to define a force, only the actions of a force, which were to alter the motion in a proportional way to the mass. So this wraps up a quick discussion of the principles that are contained within Newton's three laws that appeared in Principia Mechanica several hundred years ago. And in the next screencast, we'll start to put some math onto these ideas.